All right, so actually got a question to work one of the homework problems, so I'm going to write it up on the board behind me really quick. It's kind of what got me delayed. And so this is just the half reaction of chromate going to chromium plus 3. So with a lot of these redox problems, I saw the comment is like, I want to do the charge balance. Don't get into the nasty habit of thinking that the charges are going to kind of help you out here. So the problem with using charges is what's considered counter ions. So here we actually have a counter ion H. So if this were to completely dissociate, we'd have H plus and CrO4 minus 2, and then you could do a charge balance and make it work. The problem here is that we have hydrogen that's providing a +1 charge, and it's compensating for one of the negative charges on chromium. So the issue with trying to do a charge balance here is that you can get the right answers for the wrong reasons, and it's not apparent why the answer is right or why it's not right. So in particular, what if I added something like sodium, Na, and instead of H+, I had something like HCl. I could eliminate all the charges from this reaction so that there are no charges that can be used at balancing. The reason why we omit the spectator ions and rely heavily more on just like the H pluses and things like that is to simplify the problems, because that is a lot to digest in a single problem. What's the counter ions? What's the charges on the counter ions? So to keep the problems focused, we typically keep the ions in solution, but in reality what you would be mixing would be something like chromic acid, H2CrO4. That would give you the H+, and like you can quickly see how it stops looking a lot like these simplified problems. So the correct way to approach these problems is what I'm going to show you here, is the half reaction. And what you need to do is you need to start looking at the oxidation state. So we have hydrogen plus the oxidation state of chromium plus 4 times the oxidation state of oxygen equals -1. And hydrogen being the least electronegative is going to lose its valence. This will give you +1. Oxygen being the most electronegative is going to take a -2. So we get 1 plus the charge on chromium plus 4 times -2 equals -1. So we get chromium plus -7. 4 times -2 plus 1 is -7 is -1. So chromium here is a +6 oxidation state, and it goes to a +3. Now, the correct way to count electrons is we have two numbers. We have the number of atoms. So this is the number of chromium atoms that are being oxidized or reduced, and it's times the number of electrons, or the change in the oxidation. And this will give us our number of electrons. So we've got one chromium atom, and we're going to change the oxidation state from 6 to 3, so that's 3. So we've got 3 electrons being gained in this case in this half reaction. The rest is pretty easy, how you figure out the number of oxygens and the number of hydrogens. So we're going to balance oxygen using water. So we've got 4 oxygens here, 0 here, so we're going to add 4 H2O. Now to balance the hydrogens, we've got 1 hydrogen here, we've got 8 here, so we need to add 7 H pluses to the left side, and that will balance out the reaction. Now, a common mistake I see here is students tend to ignore these species. You need to count everything, and this is why you'll end up getting like everything else is right but this one point. It's because you've kind of like either subconsciously just ignored the hydrogen or ignored the oxygen in the molecule. So that was the only question I got in advance. Are there any other questions out there? Nernst equation discussion problem. All right, let me bring up the course. So a comment about the Nernst equation. Earlier in the semester we worked with this formula, delta G equals delta G naught plus RT ln of Q. And you worked with this for test 3 where you wanted to figure out the free energy change at non-reference conditions. So the Nernst equation is this exact same equation, it's just been converted. So here we have units of kilojoules per mole. The Nernst equation takes the delta G and divides it by minus NF. And this becomes defined as our voltage. This kind becomes defined as our reference voltage. And we get minus RT over NF ln of Q. So what the minus 1 over NF does is it does two things. One, it flips the sign. And the reason it flips the sign is we never work in negative voltages. We always work in positive voltages for convenience. So a spontaneous reaction has a negative delta G. A positive voltage implies a spontaneous reaction, so the negative switches that sign. The NF here converts us to volts to electron equivalents. So it takes us from kilojoules to mole to volts per electron equivalent, which electron equivalent is just a weird placeholder for the physics. But basically it's going to convert your kilojoules to moles to volts. And so this is all these are the same equations, they just have different units, that's it. So where do you get delta G? All right, you got a couple questions here. Where do you get the delta G from? As far as so let me go back for the previous problem really quick. The way you get the 6 on the chromium, there are a couple rules here. The sum of the oxidation states has to equal the overall charge in the molecule. So the charge is up here on the top right. And I just represent the oxidation states until they're known with the chemical elements. I'm sure you can actually see that. Yeah, that's still visible. The other rules, the most electronegative element takes the negative charge, the least electronegative element takes the positive charge, and that's as far as we can get with rules. The rules always have to be followed. The guidelines are followed as long as they don't contradict rules. So oxygen can actually take on multiple oxidation states. It can do +2, +1, 0, -1, and -2. Hydrogen can do +1, -1. There are all types of oxidation states you can take depending on relative electronegativity differences. So chromium we don't have a guideline for, but oxygen, hydrogen we do have a guideline for. And the guideline with oxygen is that if it is the most electronegative element in the molecule, it'll take a -2. So like water, H2O. Oxygen is so electronegative it pulls both electrons off of hydrogen, that gives you a -2 charge. Hydrogen, our guideline is that if it's not if it's the least electronegative element, it's going to take the +1. So we've got a 1, chromium, -2 on the oxygens, and when we solve this, we'll end up getting chromium being in a +6 oxidation state to give us that overall -1 molecule charge. Now, quite frankly, weird thing I see students doing is they try to associate this -1 with oxygen. That's not what that -1 refers to. That -1 refers to the entire molecule. So spread over the entire H, Cr, and O, there is an extra electron on that molecule. So like nitrate, NO3 - 1, there is an overall extra electron on that molecule relative to nitrogen and 3 oxygens. -1 doesn't tell you anything about the oxidation states that are in there. So to go back to this question, this is actually from test 3. So we had this expression that the real Gibbs energy based on non-equilibrium conditions is the reference at 1 atmosphere, 1 molar liquids, 1 molar gases, all the reference conditions plus RT ln Q. If we just multiply this whole equation by -1 over NF, N is the number of electrons and F is Faraday's constant, we get the Nernst equation. V equal, okay, it's not E, V, it's E, and I had to get out of this nasty habit. So we get E equals E naught ref minus RT over NF ln of Q. So the Nernst equation is just the Gibbs equation repurposed for volts per electron equivalent. It's what you've already worked with before. So to use the Nernst equation, it's pretty much the same thing you did for test 3. You need to calculate Q, and then you need to plug in the values. So let me bring up the reaction. So the reaction is 8H plus MnO2 solid aqueous plus 10 solid goes back and forth, and we do have to write this reverse reversibility arrow. It is a weird nuance of electrochem. So they're probably not going to let you use your iPad because that has an internet access. So my guess is that you're going to have to transcribe your notes by hand. But yeah, I would really say that they're not going to let you bring your iPad in simply because they can't guarantee that you can't like turn on the wireless feature, because you're going to be on a computer, but they can control your internet access on the computer. They can't control it on your iPad. All right. 0.1 molar SnCl2, 0.2 molar MnCl2. I think it's MnCl2. Yep. And 0.01 molar H plus. Or did I say HCl? HCl. So the standard reduction potential, we need to figure out what's being oxidized and what's being reduced. So your reference here is the cathode minus the anode. So reduction occurs at the cathode, oxidation occurs at the anode. Now for simplicity, what we work with is just the standard reduction potentials. And that's where this negative comes from. It's really E of the cathode plus E of the anode written as a reduction reaction. But we don't want to keep oxidation and reduction reaction. I'm sorry. It's truly this, anode plus cathode, but here we're going to write the anode reaction as if it is reduction, recognizing that if we just flip it with a negative, we get the correct cathode voltage. 720p? No, because we end up getting these weird latency issues. But I can try to pull the camera closer for you. We're just going to lose a little bit of board space. Also, let's make sure YouTube isn't doing something weird today. Telling me my resolution is 1024 by 576. I seriously doubt that. E times something. So here we've got our reference potential is the cathode minus the anode written as reductions. So we write them as reductions because the voltage of the oxidation reaction is just the negative. You're flipping the reaction. All right. So now I need my table of electrochemical potentials. Now for the final, you'll be supplied with a table. To do the homeworks, you need the really big table. That's on the course website. It just gives me options for more problems, but it's because you're doing homework. It's not because you're going to need this for the practical. So we've got two reactions here. We've got 10 going from 0 to plus 2. That's our oxidation reaction. It's losing electrons. And here we've got manganese going from plus 4 to plus 2. So this is our reduction reaction. So for MnO2 going to Mn plus 2, if you go to those tables, you get 1.224 volts. For 10 plus 2 going to 10, come on, you're in there. Minus 0.1375 volts. So the thing to keep about electrochem is that you've actually already done this. And don't try to treat this as a completely separate new topic. You've done potential energy. That's all electrochem is potential energy, but instead of kilojoules per mole, it's just volts. So if you go underneath the lessons ribbon, under the final exam, it's at the very bottom. Now, electrochem is nice to finish on because it does kind of sweep everything. From chemistry 1, you figured out how to do oxidation states because you were having to do that for the naming. So to name something like FeCl3, you treat chlorine as -1, so that gave you iron 3 chloride. And so it's just kind of building back on that old material. Yes, so the reference you have to look up. So it's like it's just like the free energies. you can't just know the free energy off the top of your head. You generally go look these things up, and we look them up under what are considered the reference conditions. Now, the reference conditions here are slightly different than what they are for the delta G, delta H. You don't have to worry about that nuance at this level. They are slightly different, though. But anyway, we want to know the reference potential. The cathode reaction, the reduction reaction, is the manganese, so that's 1.224 volts, minus the anode reaction, which is negative 0.1337. Now, this is reduction, this is oxidation. That's where this negative sign comes from, is to say that really the reduction potential is minus 0.1375 volts, but for the anode, we're actually doing oxidation. So, yeah, if you look at the table, so the table you get for the final is like 18 half reactions. The one I supply you with has like 60 or 70. There's just a lot of them. But it's the only way to make these problems like somewhat varied. So if we take 1.224 and subtract off minus 1.375, so they've been told to give you a formula sheet, but it's also available on the course website, and it's available on the assignment link that you'll be using. So even if they don't supply it to you, it's like right there for the exam. 1.224 minus negative 375. So you get 1.3615 volts as your reference. So again, you got the oxidation and reduction reaction. The trouble here is keeping in mind that you've got oxidation and reduction. You're going to subtract off the oxidation and reduction potential, convert it to an oxidation potential. But your cathode reaction is whatever's gaining electrons, getting more negative, and for your oxidation, it's whatever's getting more positive. All right, so that was question 1. What's the reference potential? Question 2, what's Q? So Q you did on test 3. It's just, in this case, concentration of manganese plus 2, concentration of Sn plus 2, all over the concentration of H plus here to the 8th power. So it's 0.1 times 0.2 all over 0.01 to the 8th power. Yep. So the E naught ref is just whatever the reference is. It's the same, it's analogous to delta G naught. So basically, what would be the voltage if we had 1 molar aqueous solutions at room temperature and atmospheric pressure? But instead of being in kilojoules per mole, which is what this is in, what would happen if we converted it to volts? So if you took the delta G naught and multiplied it by 1 over NF for this reaction, you would get 1.3115, 1.3615. All right, so if I work out Q, I get 2 times 10 to the 14th. Really? God, that's a huge number. Yeah, it is what it is. So there is the relationship that delta G equals, so delta G over is your voltage. And so your reference voltage is just your reference Gibbs free energy, your standard Gibbs free energy over NF. In here is the number of electrons. So make sure you can see that. So in here is the number of electrons in the reaction. And F here is Faraday's constant. That's 96.485. It's in, oh dear, kilojoules per mole volt electron equivalent. It's got some weird U's on it. Some books will give you 96485. Do not use that number. Use 96485. They're the same books that somehow think G should be in joules. That doesn't make a lick of sense. Not a single book reports delta G's in terms of kilojoules. They all report them in terms of kilojoules. And also, because everything's reported in kilojoules, Faraday's constant here is 96.485. But all this 96.485 is, it's a conversion factor. It converts between kilojoules and volts. And instead of being on a per mole basis like we are with delta G, that n number of electrons switches us from a per mole to a per electron basis. So this NF here is just a conversion factor. The 96.485 scales kilojoules to volts, and the N scales the moles to electrons. All right, so we've got Q, we got our reference. The next question is, what's the actual voltage? So E here is the reference minus RT over NF ln of Q. So we've got 1.3615 minus R 0.008314 times the temperature. This is going to be 298 Kelvin, all over N. The number of electrons transferred here, as 10 goes from 0 to plus 2, so it's 2 electrons, times Faraday's constant, 96.485, times the ln of Q. So this is just a plug and chug problem. You take the values that you have and you enter them in. So if I do that, I get 0.938, 0.93, we'll round to 3 decimal points, 939 volts. So that's your answer. You just plug into the formula and you get 0.939 volts. Now, few things to note about the voltage that you should be getting out. It is very hard to get away from that reference voltage, and there's 3 factors that keep you from getting that far away from the reference voltage. First is this natural log. So you got 2 times 10 to the 14 here. If I took a logarithm of it, just a log, not a natural log, I would get 14. So I took, let's see here, 2, my goodness, what is that? That's millions, millions, or millions, billions. So I took a number that was 2 times 10 to the negative 14 and crashed it down to just 14. So this Q here is going to do a really good job of, that ln of Q is going to keep large values of Q very small. So it doesn't matter how big Q gets, generally this natural log of Q doesn't really get that big. The second factor here is the 0.008314. You're already effectively dividing by 1,000 with that, and then your Faraday's constant is pretty big. So this term here really doesn't change your answer that much. And this is why batteries, even when you run them for hours and hours and hours, their voltage is still pretty close to whatever the voltage is written on the battery. So 9-volt battery will typically stay 9 volts for a very long time until you're almost ready, until the battery is almost dead. At that point, its Q value starts getting really extreme. It goes to one extreme or the other. But when it goes to that extreme, that's when you start seeing the voltage shift. But if you look at something like a car battery runs 12 volts. When a car battery dies, it's generally running 10 volts. So your car battery, after 3 years of constant abuse, pretty much loses 2 volts of power when it's finally dead. The battery still kind of works, but doesn't work very well, and it does a really poor job maintaining charges. But even at that completely degraded state, you've only lost 2 out of 12 volts. The same thing's going to be true of a lot of these. It is really hard to shift more than half a volt, and that's with really extreme values of Q. So if you're getting something like your reference voltage is 1.3 and your answer is like minus 9 volts, you probably did it wrong. But if you got 1.3 volts and your reference voltage is 1.4 volts, you're probably right. It's very hard to get very far away from this reference voltage. And again, it's this ln of Q, and it's this teeny tiny term that appears right in front of the ln Q that make these contributions very, very small. A volt is a lot of power. We don't think about it, but because we have 120 volts in our house, we have 9-volt batteries, but a volt is a ton of energy. It's just not necessarily, like, the current on it isn't very big. All right, so what's Q? Number of electrons transferred is 2, voltage at 25 degrees C. What can make these types of problems hard? Generally speaking, the only way to make these purely abusive problems is not to give you a balanced reaction. That said, that is a lot of concepts to layer into one problem. So particularly with the final exam, if you're given a reaction said, okay, what does the Nernst equation say the voltage should be? The reaction is going to be balanced. Like if you don't know that the reaction isn't balanced and you make a mistake balancing it, it's going to really start messing with these numbers. So for any type of Nernst problem, you're given a balanced reaction. The only exception is that if you go into the practice packets, there is one page, one problem where the reaction isn't balanced. It's kind of a more challenging in-class problem, but definitely on exams and homeworks, the Nernst equation is already balanced. It just kind of prevents you from making an earlier mistake that really propagates down the road. The only other way I can think to make these equations super hard is just to give you funky numbers. But so if you remember back to test 3 where you had two types of problems, you had equilibrium and non-equilibrium. The equilibrium problems, you had to build an IC table and you had to solve for the extended reaction, and from the extended reaction you had to figure out the final values. That was a ton of work, but when it came to the non-equilibrium stuff, you literally just chunked it all into a formula and you were done. The Nernst equation is the same way. No battery operates at equilibrium. If it did, the free energy change would be 0 and there'd be no driving force. So all electrochem problems are pretty much inherently not at equilibrium conditions, so there's no having to algebraically solve for equilibrium concentrations. You're just pretty much plugging into a formula. And especially with the exam, it's going to be a lot more focused. For homeworks, I kind of need to give you variety. And so that's why there's that enormous table that's been posted on the course website, so I can introduce all types of varieties into the questions you can be asked. But for an exam, we're not assessing your ability to go find one reaction to C of 60 reactions. We're asking you to figure out a reference potential. So let me... see this week on the final exam study packet. So there's actually two packets on the course website. So the first two are Redox and nuclear chemistry problems. That's the new stuff. And then the final exam review packet is literally, it's just going back to the old stuff for the test 1, test 2, test 3, test 4 stuff, so you can kind of have like new problems to practice. As far as the homework goes, there are definitely problems on that. Yeah, we can work for the nuclear half-life problem. So for WebAssign, there is balancing redox reaction, nuclear half-life, nuclear chemistry, voltage and free energy. Voltage and free energy is the discussion board problem. Oxidation states is a review from Chem 1 just to kind of get you back into figuring out oxidation states. Nernst equation, I'm sorry, voltage and free energy is not Nernst. Voltage and free energy is just converting between delta G and V just so you make that connection. Nernst equation is what we've just done. Current and mass is another one we can talk about. That's just a formula. Okay, so for nuclear half-life, there is one formula that governs them all, and it's this formula here. Oops, force habit. So N equals N naught 1/2 raised to the T over T 1/2. N is mass, moles, atoms at time T. N naught is your starting mass, moles, or atoms. T is time. And T 1/2 here is the half-life. So this is not T times 1/2, it is T sub 1/2. No, they appeared last week. They were opened up when the homework was due last Thursday. So there's two varieties of these problems. One is solving for N or N naught, the other is solving for T or the half-life. A lot of these are just plugging in. So if you look at the half-life problems on the course website, So question 6, what mass of 239 neptunium remains of a 100-gram sample if 2.356 days, if the half-life is 2.356 days and the sample is left for 10 days? So number 6 on the homework, you're being asked to find N. You start with 100, and you're told that the half-life is 2.356 days, and it's left for 10 days. So all you do is put this in a calculator. 100 times 1/2 raised to the 10 over 10 divided by 2.356. The other flavor here is finding the time or the half-life. So for these types of problems, all we do is we rearrange. So we divide both sides by n naught. This gives us 1/2 to the t over t 1/2. If we take the natural log of both sides, we get that t over t 1/2 equal times the natural log of 1/2. And then if we divide this over, we'll get the natural log of n over n naught divided by the natural log of 1/2 equals t over t 1/2. So in the first problem, it asks you what's the half-life. So it asks you to solve for t 1/2. Given 22.3 grams of a 25.6 gram sample remains after 5.23 seconds. So these are just rearrangement problems. That's it. The challenge is more when the half-life shows up here, because then you have to do this algebraic rearrangement with natural logs. But if you go through the course notes, it supplies you with both formulas. So the PowerPoints give you both this rearranged formula as well as this formula here, and then you just use algebra to solve for whatever variable you're missing. But half-life problems only truly get as hard as they're going to get if you're having to solve for like the half-life or the time, simply because you're going to have to rearrange this formula. Now, in older versions of OpenStax, which is the book we use, they used to actually go through the derivation of the half-life formula. I get why they do it, I just don't think it's useful. So the end result, that 1/2 raised to the t over t 1/2, that's the far more formula. And you're also given that on the final. I'm not going to make you memorize the Nernst equation. I'm not going to make you memorize the half-life formula. Because while they are good equations, and electrochem is important, like if you're going to do any type of renewable energy work, you need to know the Nernst equation. At this level, it's not essential that you memorize it. And I'll reiterate what I said yesterday. Balancing the redox reactions, it is the hardest concept of the new material. It's also only one question on the final. And the homeworks are hard because what I've generally found writing these types of problems is that it's either super hard or it's super easy. And with homework, I prefer to make it the harder form of the problems because you do have more time to do them versus an hour and 50-minute final exam. That said, it's hard to find problems that kind of straddle that, you know, oh, it's not so easy, you don't even need to bother to do a half reaction, to it's so hard and there's so many things that can go wrong. So the homework, that's just kind of the best we can do with the problems we have. I've written a lot of these problems, and without fail, they're either super trivial, and you can see this in the notes. They either are super trivial or they're super hard. It's hard to find a middle ground with these types of problems. But don't hyper focus and don't freak out, but don't get like super anxious over balancing redox reactions. Definitely the ones on the final are a lot easier to work with than the ones you're seeing on the homework. Nernst equation is very much plugging and chugging. You've done this before. You've done this with the delta G equals delta G naught plus RT L and Q problems. The only difference here is that you've got the N over F, so you have to find the number of electrons transferred. But you can kind of see that with the discussion boards and the homeworks. It does kind of walk you through that process. Find the reference potential, find the number of electrons transferred, now find the actual voltage at these non-standard conditions. And then the electroplating equation. So this is the electrolysis discussion board. There's a formula in the notes. You'll also find it on the exam sheet. I times T times 1.037 times 10 to, I think it's a -5, times nu I over nu E times molecular weight equals grams. So this is the electroplating equation. For any reaction, nu I is whatever you're plating or removing. Nu E is the number of electrons transferred. I is the current in amps, and T here is the time, but the time has to be in units of seconds because an amp is defined as a coulomb per second. So if you look at the discussion board, it says 1.33 amps are transferred for 1 hour, but we can't work with hours, we have to work with seconds, so this is going to be 3,600 seconds. And we want to know how many grams of iron are plated. So we've got 6 electrons, and we've got a 4 in front of the iron here because it's 2 Fe2O3 plus 6 electrons goes to 4 Fe plus 3O2. And the molecular weight of iron, I think, is 55.6 grams per mole. You would just multiply this all in your calculator. So the electrolysis problems are very much just being able to apply the formula. There is a proof in the notes where this comes from. All it is reaction stoichiometry. If we have current and we multiply that by time, we get electrons, which is how I'll explain it in course. So current times time is, it's actually coulombs. This term here gets us to moles of electrons. This term here gets us to moles of whatever we're plating, and this term here gets us to grams of whatever I is. So current times time is coulombs. Coulombs times 1.037 times 10 to the -5 will get you moles of electrons. This mole ratio here will get you to moles whatever you're plating, and then the molecular weight whatever you're plating, that'll get you to grams. But all it is just a conversion factor between coulombs, which is where your amps are in, to grams. And I did actually prove this the first semester I taught this course. It's like, this is a surprisingly elegant formula. Again, I don't know if it's 10 to the -5. You'll need to check. I don't know the formula off the top of my head. I know it's 1.037, and I think it's -5. It may be -4. You should be getting about 1.8 grams when you do this problem. And then balancing nuclear reactions, honestly, you probably did this in high school. If you have issues with it, please feel free to ask. The only rule is all the top numbers have, on the left side, have to add up to equal the top numbers on the right side. Same thing's true for the bottom numbers. I am a stickler for charges, nobody else is, and I don't enforce it on exams. It's just my little pet peeve with textbooks that they throw an alpha particle out there as +2 is like, you know, those 2 protons were balanced out by 2 electrons. That's just my weird little thing. Yes, 4/6. So VI over VE. It's not an S, it's an E. So E here is the number of electrons. And that's given to you in the half reaction. Then the only way to make these types of problems hard is not to tell you the number of electrons, to force you to figure it out yourself. But it's just a formula. Oh, and I can also give you time and not seconds. So I'll reroute so it's a little bit clearer. Again, I don't know what this power on this number is. I know it's 1.037. I'm really pretty sure it's 10 to the -5. Yeah, I is current, T is time in seconds. Nu I is whatever you're trying to convert to in the reaction. E is the number of electrons in the half reaction, and molecular weight is the molecular weight of whatever I is. Which for iron, I think it's 55.6 grams per mole. So if you're not given the half reaction, so this iron problem is actually a really good example of this. So let's say somebody just gave you this reaction and they didn't tell you the number of electrons, which they should because it's not balanced as is. So two numbers get multiplied together to give you the number of electrons. The first is the number of atoms. So on the left side we have 4 iron atoms, and on the right side we have 4 iron atoms. So each one is gaining or losing electrons. So there are 4 of them. And the number here is the change in the oxidation state, or oxidation number. So here iron is in +3, here iron is in 0. It's weird. And so it may be wrong on the discussion board. Is it really Fe2O3? Cool if it's wrong on the discussion board. Change that next semester. Actually, it should be 12 electrons, but whatever. So in this case, we changed 3 electrons, so we have 12 electrons. Now this is the important part here. It's 2 numbers multiplied together, not just the change in the oxidation state. And the example here is that if I have $10 in my wallet and you have $10 in your wallet, how much do we have? And if you say, well, we got $10, that's wrong. We have a total of $20. So it's not the number of electrons gained or lost by individual atoms. It's the number of electrons gained or lost by all the atoms being oxidized or by all the atoms being reduced. Back this back up now. Yeah, I think that's just a typo on the discussion board. I've still been, the way I wrote the key assumed that the 6 was correct, and you don't need to know that that's incorrect. So if you use 6, that's fine. It should be 12. I think it's just a typo. Send to correct for next semester. No, it doesn't matter what calculator you use. In fact, that was a question I got asked when I set this up. They said, well, TI-34, TI-82, 83, 84 is whatever calculator you want to use is fine. You honestly don't need much above a TI-34, but a TI-83, 84, that should work just as well. You're welcome. So vapor dependence. So I think you're talking about how vapor pressure changes as a function of intermolecular forces. So as intermolecular forces increase, the vapor pressure actually decreases because it's holding onto its vapors better. That's the only thing that decreases with increasing intermolecular forces. So boiling point increases, freezing point increases. What were the others? Viscosity increases. All those increase with increasing intermolecular forces. Vapor resistance doesn't. I'm not sure what you mean how to find a given reaction. Okay, so pressure dependence of a given reaction. So there's a quick way and a fast way. Quick way and a longer way. The longer way gives you more information. The pressure dependence for a reaction rate is just the sum of the gas phase species. So let's say we have 2A gas plus B liquid goes to C. And we want to write our reaction law R equals K A squared B. So the pressure dependence is going to be the sum of all the gas phase species. So let's add a C in here and let's make it a gas. So since A and C are both gases here, this would be a third order pressure dependence because we got a gas here and a gas here. Now let's say 2 is actually a liquid. In this case, we would go down to a first order because we've only got one gas. Now, if we want to write the rate law in terms of this pressure dependence, first thing we would do, let's put these all back to gases. For everything that's a gas, we would replace it with its mole fraction. And then we would raise P naught over RT to whatever the number of moles of gas are. So we got 3 moles of gas, so this would be P naught RT to the third power. All right, so we're coming up on the end of the live stream. Thanks for the questions. We have 2 more live streams, so live stream tomorrow, live stream on Thursday. They're not going to stop because it's the final exam. Please feel free to email questions in advance if you got them. I'll talk about anything. I will get a little guarded on Thursday for questions just in case some people are fishing because they're currently taking the final exam. But generally speaking, please feel free to come and answer questions. Today you have the homework due, the last lab due, you have the discussion boards due. Tomorrow the plan is to get up, download the remaining grades off the website, and so this way you can have your homework grade and you can have your lab grades tomorrow so you kind of know what you need to have on the final. All right, thanks for showing up, and I will see y'all tomorrow.